Yeah, thanks for coming for this talk. This is a joint talk between me and Jeremy Soller. We're going to be talking about the Rust language and the implementation of a microkernel stack called Redox, which is Jeremy's baby. The way we're going to do this, and I'm conscious that we don't have a lot of time, the way we're going to do it is I'll do a bit of a backgrounder, and then I'll hand over to Jeremy, who'll talk about the design and the philosophy of Redox. And then at the end, I'll come back in and talk about some of the work that's happened with ARM, as in Redox for ARM, right? So I'm Robin Randhava. I work for ARM at Cambridge. I'm in the system software architecture team. I'm responsible for the safety track. The charter of this track is to promote the uptake of ARM IP in safety-critical domains using open source software as a medium. The areas I look at, internally within ARM, we keep thinking about system architecture designs with safety extensions, so I'm a part of those discussions. If you've been coming to the Linaro Connects for the automotive BOFs in previous Connects, I run the BOF. And what I've been trying to tell people is that in the safety-critical domain, all the proprietary operating systems are microkernels. So microkernels have properties that are safety-friendly, and that's an area of intense investigation in the system software architecture team. I'm particularly fond of formally verified microkernels. There's a lot of work we do with particular open source communities in this space, and also the University of Cambridge. I believe that formally verified microkernels, although not perfect, significantly raise the bar when it comes to removing human-in-the-loop test validation cycles, right, and have more machine-checkable correctness. I'm working with the AutoSAR consortium. AutoSAR is a consortium that's designed to produce interface specifications that allow different bits of software to work together on cars. I first heard of Rust, the language, actually in a discussion around AutoSAR. Now, this talk is actually about the last bullet point, safety-themed languages, runtimes, and tooling. Through this week, you might have heard that ARM has been introducing architectural extensions for safe, secure operation of software. That's for the large part designed to get legacy software running. Now, I would like to see what, if you start with a clean slate for new software, and there's a lot of new software being written even now, how can that benefit from some of the new languages and the runtimes and toolings which are safety themes, such as Rust? So I started thinking about, okay, microkernels and the ARM architecture, that's on my plate. I need to try and explore that space and learn more. But then I said, let's also consider the Rust language and find out whether the language has the support it needs for running well on ARM in the different processor profiles, Cortex-M, Cortex-R, and Cortex-A. Then I thought, like, since I am doing the microkernel investigations and since I am looking at Rust, the safety language, why don't I convolve the two and reason about how good is that from a safety standpoint? How better is that? But then I thought the one really nice way of doing it would be to actually write a microkernel in Rust, right? So that became a bit of a focus area. Now, why would I want to do that? Because when I first read the kind of the Kool-Aid description of Rust, I didn't believe it. So I wanted to test the claim that Rust is a capable systems programming language, which means that I should be able to use it to write bootloaders, kernels, drivers, all of that kind of stuff. But most importantly, I wanted to do this so that I could have that sandbox I needed for my architectural explorations in the system software architecture team, which required me to have a microkernel. So I began writing one, but thankfully I hadn't gone too far when I found Redox OS, thanks to the Rust community. That's Jeremy's baby, and I'll let him speak about it, but I think it's a little unfair to actually jump into a discussion about a microkernel written in a new language without actually talking about the language a little bit. Now, this is hard. What I really wanted to do was describe the properties that make Rust safe, and that requires a lot of example source code and walking through the examples. We can't do that in this session. Maybe in a follow-up Connect, we can give that more justice. So I have some texty slides over here that will give you some keywords and some guidelines that you can use to actually learn about Rust in your own journey with Rust if you choose to go down that path. So this is the blurb on rustlang.org. Rust is an open source systems programming language that runs blazingly fast, prevents segfaults, and guarantees thread safety. That's the absolutely essential hello world blurb over there. It's a curly brace language. So mutability, right? Now this is the bit that was surprising for me, and it is also a very essential part of the language. All data in Rust is immutable by default, right? What that means is, in this example, I'm declaring a variable called var of type unsigned 32. In Rust, you have the name of the variable first and then the type, okay? I initialize it with 0 and then I attempt to increment it. the compiler whinges. You can't do that because you forgot to declare that variable as mutable to start off with. Now, why is this a big deal? Because if you look at the CVEs, you'll find that a lot of concurrent software has problems because programmers weren't disciplined enough about figuring out what shared mutable state needs to be shared concurrently, right? In many cases, a lot of data that does not need to be shared, but it's exposed because they didn't use const, because why would you, right? Rust is forcing you to do that. Right? Small thing makes a big difference. Ownership. Now, this is the bedrock upon which the entire safety play in Rust works, right? There is a notion of ownership that's tied to function scopes, right? You have mutable types and immutable types. You can only have a mutable type used in one scope, right? This is the bit that's really hard to explain without diagram or with some source code, right? So if there's a function and within that function you declare a variable, that function scope is the owner of that variable. If you decide to make a function call where you decide to pass that data item as an argument to that function call, you are relinquishing ownership from the calling scope to the called scope, right? From that point onwards, if I carry on in my scope and terminate, nothing happens because I'm not the owner of the data that was allocated for this particular data item. However, the function that was called, since it is the owner, once its scope ends, Rust will intervene and actually do automatic deallocation of the reserved memory, right? So that happens automatically. You can have mutable types only in one scope at any point in time. Immutable types you can have across multiple scopes because that's okay, right? Now, you don't always want to copy data back and forth, so you need a pointer-like reference scheme, so you have references. You can pass a reference to a data object into another scope, but references also have mutability and immutability as a concept, and the same rules apply. You can't really have more than one mutable reference across multiple scopes. This may sound complicated, but actually it's blended very well into the language, right? The critical thing is these rules are checked by the compiler for you. Right? And these rules apply even in truly concurrent executions where you have threads. If you have threads and you're talking about the entry point of the thread being passed some data or the thread making an access to global state, the same rules apply and it's checked at compile time, which I think is very cool. Thanks to this, you have none of these typical classes of errors. You don't have use after free, use before initialization, null pointer dereference, double free. Rust's semantics and syntax force you to actually service each and every expected return type, return value from a function. You can't say that the classic programming problem is that, oh, this is the result I expect from this function, so I'll check for that return value and act on it, but I forget to figure, to service the error condition that came back from that function potentially. You can't do that in Rust. It's a compile time error. You even have, at runtime, if you oversubscribe a buffer, that's a panic. Initially, I thought, why can't you just deal with that at compile time? That's harder to do, and that has performance implications, so they do it at runtime. So why is it better than C or C++? Because in those cases, if you oversubscribe a buffer, something bad will happen because you overwrote the stack, and you'll never know unless you actually hit it, right? Rust will consistently give you a panic at that point in time, which is way more consistent. Type width clarity, simple thing. I personally, in my professional career, have been bitten by this one. C99, they are ambiguous. They don't really tell you what is the type width for some of the types. Longs in particular, are they 32-bit, 64-bit on your particular architecture? Don't know. The type names in Rust encode the type size. No arguments, very clear. Threads are a first-class language item. Unlike C or C++, in C++'s case, you need to resort to boost. Or with C, you need to resort to some pthreads implementation that you call into. There is a thread keyword, and there is a thread library, part of the standard library. Threads are a first-class item. This is a very simple example where there is a mutable, key point on mute, mutable vector called children. It's empty. I use it to store the handles that I get from spawning threads. That's the standard way of spawning threads, std thread spawn. You give it a closure. A closure is like the entry point, the function you want that thread to execute. And once the threads have been spawned, you just iterate over the children vector and join them up. Just a contrived, simple example, right? Yes, yes. Yes. So a very rich standard library. All of the stuff that I would associate with kind of interpreted languages like Python and Ruby, right? So all of those things are actually part of a system programming language, a compiled language, right? Which is quite refreshing in my opinion. Map sets, linked lists, dictionaries, it's all there. Platform abstractions, sockets, TCP, threads, shared memory types. And the really cool bits are the functional language bits like closures, iterators, generators, pattern matching. Idiomatic Rust code uses a lot of the functional properties and just makes for cleaner code in my opinion. This is another really good one, right? So you can't forget to take a log for mutable shared state because the data that you intend accessing with a synchronization primitive is owned by the synchronization primitive. If you forget to use the synchronization primitive, the compiler won't compile that program, right? That's it. Simple, straightforward. Yet another way to prevent bugs. Now, of course, if you want intentionally to violate the safeguards provided by the compiler, so a lot of the times you need to do that, you have a technique there. There is an unsafe keyword and an unsafe block. You put your code inside an unsafe block, the compiler won't do all of its magic. If you're doing operating system development and you want to write to a system control register, you want to use inline assembly, that's an example of an unsafe operation. You put it inside an unsafe block. The first thought that came into my mind was, oh my God, now I have to write unsafe. Like most of my operating system for backend for a particular architecture is going to be unsafe code. But really, this is all about labeling clearly to the compiler the bits that are quite likely to be the root of problems, and that makes a static analyzer's job really straightforward. Right? Atomic types. Atomics are supported by the language. They form basically the building blocks for communication between threads and concurrent types. Like C++11, you have the ability to express the desired memory consistency for loads and stores to atomics, which is also kind of cool. Rust doesn't claim to have a perfect story over here. It rides on top of the memory consistency architecture and expectations that LLVM has, right? So it's as correct as LLVM does it. That's about it. Mark's looking at me. I'm going to ignore him now. But we can come back to this. Over here, basically, there's a variable that's declared as an atomic use size. It's wrapped up and treated as a spin lock. And you're trying to do a store operation to claim the spin lock, or in this case, clear it. You can specify the kind of ordering you want for this. Again, for when you're writing operating system code, when you want to do like a scheduler or something of this sort, this is nice to have over here. Concurrent Rust programs do tend to be faster than the C and C++ counterparts. This is because of the compile time checks, the ownership checks. They remove a lot of the boilerplate that you traditionally have with concurrent programs, where you have to explicitly test for correctness. Is a pointer valid or not? Do I have the right lock, et cetera, et cetera. Since that is gone, you end up having faster programs. And this is just a contrived example I put over here, but this is a really nice program called ripgrep, which I use. Try it. You won't go back to grep. It's super fast. And the code's very clean, too. So now I'm going to hand over to Jeremy, who's going to tell us about Redox.
Yep. So Robin set up the language, but I'd like to set up the other foundations of Redox. Beyond Rust, we also have Unix, GNU, Linux, some other projects that were really interesting. Then I'm going to go into Redox at the high level, and then I'm going to specify the roadmap, what kind of community model we have, the microkernel, Userspace, and I'm going to go through an example driver. Now, I was going to show a live demo, but I probably won't be able to do that because of time. I'll have to use it? Okay, yeah, that's fine. So Unix, the name derives from Multics, which is an earlier multitasking operating system. Unix is multi-user and multitasking. Development began in 1969. It has Unix philosophy, which covers many different things, but modular philosophy is one of those things. So do one thing and do it well. This comes back for Redox in very strong force. It has a simple file system with a unified namespace. It has simple file system. It has simple system calls, most of which are based on file system calls. Everything is a file to the kernel, and all of the calls are related to file handles. Has a powerful shell where most programs can be scripted, and it was a pioneer in portable operating systems. It was written in C, so it was able to be ported to many different platforms. In many ways, it's divine. It was the starting point for many of the operating systems we see today, including Windows, which utilizes the C programming language that was actually invented for use in Unix. The creator is 75 years old and has the most majestic beard you could ever find. GNU, the name originally meant nothing. It's the name of the animal capitalized. But Richard Stallman came up with a backronym. GNU's not Unix. Well, GNU is Unix. GNU is a free software implementation of the Unix components. It was developed by the Free Software Foundation in 1984. They wrote most of it in C, and they also developed critical free software licenses when they were developing GNU, such as the GPL. They developed a microkernel called GNU Herd that has gone almost nowhere, and they also developed a very large number of projects. We're talking GCC, bin utils, core utils, things that are very common across all free software operating systems. Usually GNU is paired with Linux. The creator is 65 years old and has a pretty okay beard. Now, Linux. Everyone here, of course, knows Linux because ARM and Linux go hand in hand. Everywhere they go together. They go to mobile, they go to embedded, they go to IoT. Wherever Linux is, ARM is as well. Linux was created by Linus Torvalds in 1991. The name comes from his name mixed with Unix, which originally he thought was too egotistical. When he uploaded it for distribution, the person running the server renamed it from what he had originally wanted to use, which was Freaks, F-R-E-A-X, to Linux, which I think is a much better name. It's written in C. It is a free Unix-like kernel implementation. It's the de facto kernel for GNU Userspace, and it has completely dominated all computing markets except for the desktop, which is something we're working on. The creator is 48 years old and has a pretty appalling beard compared to the last two people. Now, honorable mentions. Some of these are actually more influential to Redox than the past three, but the past three are much bigger projects. So I'd like to go through FreeBSD. Capsicum was an important reference for our capabilities-based design. Minix 3 was also another important reference. They have kernel-facilitated memory-mapped IPC, which is something we utilize as well. They have a reincarnation server that we're thinking about implementing on our own to restart failed drivers. NetBSD has a package management system that we used as our base for our own package management system. And they also had this idea of a rump kernel, which would facilitate user space drivers that could then be recompiled for a monolithic kernel and could actually be ported between kernels. Plan 9 is one of the biggest influences. It's listed almost last, but what Plan 9 had was a unified namespace where you could find everything, including networking, which was something that Linux and BSD and other operating systems continued to do through separate system calls. Plan 9 started to do through the unified namespace, which is something that influenced our design. And then Smart OS. They have a concept of zones that really went into what we wanted to do with namespaces, which I'll talk about later. Okay, so after going through that, let me go through all the 200, 300, 400 different Unix things that have shown up. If I were to show this in full scale, I believe I would require probably 24 projectors wrapping around the whole room. The point is that there is a large amount of content out there to pull ideas from. And there is a very rich history of Unix and Unix-like operating systems. And that all leads to what we have today, which is the person standing in front of you. Redox. So that was a very long-winded thing, and I'm probably going to have to drink some water. What is redox? So the name comes from the chemical reaction, reduction oxidation. Rust is a redox reaction, and it kind of sounds like Unix. Development began in 2015. I was originally wanting to do anything in Rust because I had just learned about the language, and what I found was a lack of things at a kernel level, so I started writing what was originally a monolithic kernel, and then I realized, hey, you know what? would be really easy would be cutting out pieces from this kernel and moving them into Userspace. So from there it grew. And it's a MIT licensed. The majority of components in Redox are MIT licensed. Some are GPL. Those are usually things that we've ported, things from GNU, things like that. It utilizes a microkernel. All drivers and services are in Userspace. When we say everything is a file, we really mean it. It keeps Unix system calls, but it reduces the set significantly. So what that means is that in Redox, the majority of operations go through file system calls like open, read, write, seek, and close. And we also have memory mapping to improve performance. We use Rust throughout the entire project to reduce vulnerabilities and improve reliability. We have a Rust rewrite of most Unix components, and we provide a complete POSIX-compatible C library for legacy applications. And I'm 26 years old. So what is our roadmap? Well, initially I wanted to replace what was running on my own laptop and start running Redox. That hasn't gone very well. But we'll see where that goes. The desktop is a really hard target because you think about hundreds of different peripherals, and many of them require custom drivers. So we set our sights for a much more practical target, which was embedded systems. That's our current focus. What we believe that we can do is have a really world-class operating system for IoT, for embedded devices, and for servers. And we believe we can do that through a set of very simple steps. We improve the current drivers. We implement more drivers. We develop an opt-in watchdog for programs, which will be able to implement the Minix reincarnation server. And we improve SMP scheduling. And after we do that, we have pretty much all that's required. The Redox community development is done entirely on GitLab. Real-time discussion is done on our chat server, our Mattermost server. Other discussion, we have a forum. Across those 3 different platforms, we have we use the Rust Code of Conduct. We have a contributing guide for people who want to contribute. And all of that information can be found on the website, redox-os.org. Okay, finally, geez, I wanted to get to the meat. This is what I really wanted to show you. So the critical element of Redox, I believe the thing that expresses its personality most is the microkernel. The microkernel is written in Rust. It has very high reliability, and some of that comes from Rust, some of that comes from the reality of being a microkernel. Writing it in Rust allows us to do some compile time verification, not to the level that SEL4 has, but we do have a kernel that implements more things than SEL4 has. So it is a little bit larger as well. It introduces a concept of kernel or user space implemented file systems called schemes. So what this means is that you have file systems like the network file system and the, oh, that's interesting. The network file system, TCP, UDP, implemented by one application. Then we have a disk driver that might implement a file system actually to present a disk or a set of disks. We have a file system driver that presents what you would traditionally think of as a file system. And we have things for IPC that are also done through the file system. Memory mapping is done through the file system. IRQs are handled through the file system. Everything goes through the unified file system. And because of this, we limit system calls to only those required to interact with the file system, and some additional ones for managing processes. So we have open, read, write, close. We have memory mapping. And what this allows us to do is construct a very concise security model around a user space. We provide primitives for drivers. Those are also those things like physical memory access and interrupt handling, those are also done through the file system. We support containerization through namespaces. So because every operation is done through the file system, the only thing you have to do OS level virtualization is to filter the calls that an application can make into that unified namespace. So if you want to write a firewall, the only thing you have to do is intercept the calls going out from an application drop the system calls with an error like eaccess or eperm that you don't want to reach the network, and pass through the ones that you do allow. This allows chroots, for example, in jails, which are other operating system concepts, to be built on top of namespaces very quickly and easily. Processes can also enter a capability mode by entering the null namespace. What this means is that the system disallows that process from accessing any of the namespace that it hasn't already opened. This prevents a process from gaining capabilities that it did not have at launch. The kernel is 20,000 lines of code, which is large in comparison to other microkernels, but we believe that 5,000 of it could be moved into Userspace, that's ACPI code, and additional code might also move into Userspace. It may already be feature complete. This is contingent on what we find as we investigate, as we port more applications, things like that. It does appear to be feature complete. This is what we can get today. So we have disk drivers, file systems, network drivers, network stack, graphics drivers, graphics stack, pretty much everything else you would expect from an operating system. It's not as mature as what you would find with a Linux desktop environment, but it does demonstrate the power of the microkernel and the ability to implement a user space and give you an idea of what could be implemented in the future. So here we have an example of running a graphical environment. We have, I like the background so much that I only launched one thing, which was stupid, but there's a calculator running. We have things like that. We have a simple browser called NetSurf that uses SDL actually to, for graphics output. We haven't ported toolkits like GTK and Qt, but those will come eventually. How does this look at a systems level? Well, the Redox, this is a little hard to see. At the top we have the Redox kernel. The Redox kernel creates some of its own schemes over here. It launches the init process, and it loads a number of user space binaries from the init file system. So the majority of these things are done in user space. Then the initial file system loads the disk drivers and file system driver. After that, it jumps into loading drivers from the file system. Those drivers include things like random numbers, PTYs, audio and USB and networking. Then the network stack is loaded. And then finally we have this, which is the graphical environment being loaded. So now I'm going to go through an example driver, and this is extremely technical, but at the same time I think it has some kind of readable elegance to it, provided that you already know a little bit about Rust. Just click it. Yep, it should. Yep. So we have a number of boilerplate items that we have to go through. At the top we have some imports, but here's the real meat. The entry point in Rust is the main function. It can return a result, which may come from a failure of one of these calls. The first thing we do is we create a new file system by actually creating a file inside of what's called the root scheme. The root scheme is an index of all of the file systems. So if you want to create a new one, it makes sense you create a file inside of the root scheme, and then you start reading system calls from that file and writing responses to it. Next, we're going to start reading IRQs. We read from the keyboard IRQ on x86, which is number 1. We set these files up as non-blocking. We're going to create an event queue, which is opening from the event scheme. And then after we've opened all the files we want, we're going to enter into the null namespace. So this disallows this program from opening any more files. Now we add those two files that we created for the scheme and IRQ to the event queue. We set up a scheme handler that we'll talk about later. And we create a list of blocked system calls. These are calls from other processes that we have not returned a request to yet. So this is you have an option of doing asynchronous or synchronous I/O using the scheme interface. Now we loop on events. Every time we get an event, if it came from the scheme, we're going to read a packet from the scheme, and that packet is going to include information about what system call was executed by the process on your file system. And if it was an IRQ file that we had to read, we're going to read an IRQ counter. And if we caused that IRQ, we're going to acknowledge the IRQ. This allows multiple drivers to share an IRQ, which is an important part of the system. And then for every remaining blocked packet, we're going to continue to loop on checking whether or not those blocked packets can be unblocked. So this is all done in the logic for blocking and unblocking is all done inside of the scheme. So I'm going to go up one directory and check that out. So we have a trait. In Rust, a trait is kind of similar to, well, it's a list of functions that you have to implement for a specific type. So here we have to implement open. We're going to allow any path to come into open, and for every call to open, we create a new file handle and return its identifier. That identifier will then be used in the future calls to the file system. This file system is extremely simple. It only implements one system call read. So every time a process attempts to read, if the number of IRQs that we have received has increased since the creation of the handle, we're going to write a hash to that file descriptor. And this is, you'll notice that this looks very similar to the read function in C. You have a file identifier, and you have some buffer that you're going to write the information into. This is by design. We wanted to have a very high-level interface, even though we're creating a microkernel. And finally, we have implementations for fsync and close. Fsync is a no-op in this scheme, and close is something that removes the handle. So at this point, I was going to demonstrate the scheme in reality, but it's not possible to do that with my laptop at the moment. Yeah. I think you just have to hit the X up there in the corner. If you go up to the top. 30 minutes of closing applications was all we required to have things ready. Slides.google.com. Yeah, that's gotta be it. It's the right one. Oh, sorry. Okay. All right. Really? What's going on with your system, man?
Dude, your laptop didn't boot.
Yeah. Turns out disabling the graphics card on your laptop's not a good idea. Yep. All right, so Redox runs on real hardware. I was going to create a better picture than this, having all the System76 lineup running Redox, but I didn't have time. What we support is graphics through EFI or through the BIOS. This gives us a frame buffer that's typically native resolution. We support networking through a number of different devices, through the E1000 and Realtek 8168 and a number of other devices that are fairly common. And we support audio through Intel HDA. So this allows us to present a pretty complete user space for a desktop environment on most systems, and a pretty complete user space for most systems that are virtualized, because we have support for all the hardware in common virtual machines. So after running through this, I'm going to hand it back to Robin for the rest of his presentation.
Thanks. I hope this is the right slide deck. We'll know soon enough. Yeah, so as I said, I started trying to figure out how to port this into my environment on ARM. As it stands today, it targets the AR64 execution state exclusively. There are three platform targets that are being developed in parallel. The core work is happening on QEMU system AR64 with the word machine. We have students who are using a High-Key 620 and a High-Key 960 board to actually do the follow-up work, bring up on silicon. So just wanted to provide a very quick view on how I kind of went ahead with this porting exercise. It took me about this is done in my spare time, so I spent like about 2 months just learning the vocabulary, speaking to the Rust and the Redox guys. And then I published a document on the GitLab, on the Redox OS GitLab, one of which was my take on the sequence I wanted to follow to actually go ahead with the port. So that's porting the core Redox kernel to ARM AR64 outline. And after a while, I followed it up with a companion document, which is working with the AR64 port of Redox that tries to describe how to get to the current state of play. It's fairly involving, I should add at this point, because you have to get the compiler tool chains, you have to create the boot flow, and this is one area where I could do with more help over time to try and make it simple. So the first thing I needed was the Rust compiler and LLVM did not have support for a new OS triplet for AR64 Redox, so I had to add support for that triplet. I then ran into a problem because you have a thread local decorator in Redox and in Rust actually, and Redox uses thread locals for per CPU data objects in the kernel side, but I could not get LLVM to emit the right instruction. It always emitted TPIDR_EL0 references, whereas for the kernel I needed EL1. I had to figure out how to do that. I got some help from the community for that, and that works now. Just a simple triplet support to bin utils once you get your head around bin utils. System call venues for AR64 and newlib. When I was working with this, there was no relibc. I mean, it was kind of in progress. Relibc is the C library that Jeremy and company have produced, which is written in Rust. So I'm going to move away from newlib to relibc at some point. Then I hit a bug with GDB. Somehow GDB just stopped supporting debugging, well, basically kernel code, anything that has virtual addresses that are in the TTBR1 range. But again, Linaro helped with that. I reported the problem, it's been fixed now. So my debug flow is basically, for the core work, it's all on QEMU. So I'm using, QEMU happily has like a word machine kind of target, like QEMU ARM64 dev config. I modified the build glue in Redox to actually give me an AR64 build. There are some dependent libraries that had to be modified to introduce AR64 inline ASM bits, etc. Ultimately, I use U-boot as the BIOS for QEMU system AR64. I use TFTP and kernel scripts, U-boot scripts to actually fetch a file system and launch the kernel. And after the GDB bugs were resolved, I could kind of debug the kernel using GDB and QEMU's GDB stub. So porting the kernel itself, I did some early init code which does pretty classic stuff. EL2 to EL1 handoff, should that be required. I needed a diagnostic UART, so early page table setup for that, and also for mapping in the kernel itself once the MMU is enabled. I rely on DTB exclusively, device trees. This might change because Redox does have EFI support. Basically, the device tree is provided by U-boot and relayed to the kernel. I create some mappings for that. There's art-specific kernel code that I then started writing, page tables, descriptors, access control through those tables and descriptors. And I'd heard of recursive paging a while back. I remember bugging Mark about that. Somebody else was trying to do recursive paging on AR64. I thought, here's my chance to see whether I can try to use it. It's different. I know Joel asked me to, he's here? He's not here, okay. Joel from Google wanted to know more about it. Don't have time for that now, but you can come and speak to me. Then it was context management code. ELF parsing loading logic was already available in the generic bits. I just had to do some modifications for AR64. And then the meat of the fork clone exec, context switching signal dispatch, creating init context and launching that, and then the syscall exception entry decode dispatch stuff. Some in-kernel driver stubs to support timers, diagnostic UARTs, and GigV2. User space drivers, they had a PCI driver already in Redox, so I just took that and made it work with a very simple QEMU ECAM model. So it's not really a very fleshed out PCI driver. It's actually not a driver at all. It's just an accessor. But then I got the AHCI driver in Redox to actually work with QEMU's AHCI controller bits, and that way I have SATA disk access for the root file system. And it's Redox FS, which is a file system that Redox has. So I'm currently bringing up multi-user login in shell. Single user is kind of working. And after that, I've done some hacks with device trees, but one member of the community has written a scheme, like how schemes the way Jeremy described them. A device tree scheme would make my job a lot easier. I'll just convert all the drivers to use the scheme. I can just ask it for, use some semantic expressions to get information about any driver's device tree data that I needed. Frame buffer driver, very simple at the QEMU level, but we do have one open item, which is an Intel frame buffer driver for someone to do. I'll see how I can leverage some of that work. HiKey 620, HiKey 960 bring up is happening in parallel, slower than I'd like, but it is happening. And I mean to do a big documentation update on GitLab because the current documentation is about a month old. SMP support mechanics are there in Redox, but there are some problems with that, and they definitely haven't been enabled on AR64, so I'll try and work on that in my spare time. And then there's parity. That'll get me at parity with the x86-64 port, basically, right? So that's it. So we have 5 minutes for questions. Leo?
I have two questions. The first one is that the Userspace, the license is, what's the license?
MIT.
Okay, so also need to follow up the MIT.
Yep.
Okay, the second question is that actually now I can see that almost the memory modeling, the related details seems like I need to hide into the compiler, right? Because there have many the memory related operations seem like to be controlled by the compiler, for example, LLVM. So
you get the option of basically using the language primitives for the memory ordering, okay? But you don't have to use it.
So means that there have some of the optimization, for example, for the memory optimization, for example, spin lock, the release, not acquire store release, so such kind of the memory modeling related, should compiler aware that a lot of.
Yeah, so basically Rust is explicitly at this point in time coupled with LLVM. LLVM supports different target backends, different architectures. Just like any other compiler, there is an expectation in terms of the memory model, and LLVM has an expectation from AR64. Yeah, I mean, if you want to use the atomics, and if you want to use the atomics using the kind of high-level Rust primitives for expressing the consistency, LLVM will translate that into the appropriate thing for AR64. But you don't have to use that. I mean, if you have very specific concerns, you can just use unsafe blocks with inline assembly to use the barriers of choice, that kind of stuff, right?
Yes, as you say, but all drivers are implemented in Userspace.
That's right, yeah.
If you have a platform that needs real-time guarantees, how can you enforce it if it's in Userspace? Because you'll have latency, I guess, between switching a different exception level, etc.
This is something that we were thinking about working on with the watchdog timer, and that would be the ability to specify exactly when a driver would have to respond, or else it would break the rules of the system and potentially be restarted.
Yeah.
So getting into the real-time space, we will probably involve some rules around what Userspace can do, and may involve a separate spin of the kernel for real-time.
Okay. Additionally, what kind of scheduling policies do you support right now in the microkernel?
Currently, for SMP particularly, it's naive and it's round-robin. So working on the SMP scheduler is one of our highest priorities at this point.
Okay, and last question. well, right now you use it as a normal OS. Is there in the future a possibility of making the microkernel being used as a hypervisor in the future?
This is something that's up for debate, and the answer is probably so. Right now, we support a level of OS level virtualization that I strongly believe that most applications would not need to use a hypervisor with the current Redox model, but I do believe it would be possible to support that, yes.
Just two things. On the atomics front, earlier Robin mentioned that the Rust language follows whatever LLVM happens to implement. So what semantic is that targeting? Is that targeting like the C11?
Yeah, it's similar to...
Similar. So is there a well-defined semantics for those Rust primitives, or is that something that's not settled yet?
They're well-defined, yeah.
Whatever is the guarantees that GCC and company like that have, and LLVM has emulated that, and that's what is exported to Rust. But I must confess, this is not an area that I've actually dwelt upon a lot, right? And I'd actually like to get some insights from you, because you understand the atomic space really well. It's a discussion I'll take offline with you.
And one of the other things that we find, at least in Linux kernel, is really a painful area that language doesn't give us any help with, is all sorts of asynchronous behaviors from the CPU, like TLB fetches, cache prefetching, eviction, and so on.
Yep.
Is there any attempt in Redox OS or in Rust to try and model that kind of thing from like a resource ownership point of view?
Absolutely. So our page table is done at a pretty high level in terms of abstraction. Robin implemented it on ARM, and he may have some comments on paging in the Redox kernel.
Yeah, well, paging is fine, but when it comes to the kind of microarchitectural hazards that he's talking about, we simply haven't had a chance to explore the problem space with Redox.
Yep.
And we had a chat about this, and I did tell him here be dragons, because he has tried to come up with a high-level abstraction for the kind of TLB and cache maintenance required when you're doing things like tearing down page table, et cetera, It may work, but we'll only really know once we get the silicon bring up going. That's when the dragons will come.
Yep, and getting the scheduler a little bit better for SMP would help a lot too, because a lot of those TLB shoot down scenarios really only happen when you have a second processor.
We find that lots of these actually happen on single processor.
Well, then we've solved those issues, for sure.
Okay.
Yeah.
Yeah, I think silicon bring up is the, I'm waiting for that actually, because I think that'll mean we'll have to rethink a fair number of things around these, some of these assumptions, but yeah.
One last thing, so you mentioned running under QEMU, so have you run under QEMU in TCG mode or QEMU in actual virtualized KVM?
KVM for x86 and
TCG for AR64.
Yep.
So. Yes, that's part of the plan. Anything else?
Another question that I saw the slide that said don't handle the from the exception level 2 to exception 1. So this means that the kernel Userspace actually run in the year 2 and the Userspace run in the year 1.
I didn't want to assume that the bootload environment has put me at EL1. I just wanted to ensure that I can. That's it, really. Okay, cool. Thank you. Sorry.
Yeah, got a question for your statement of the Rust language. I saw you say that you can make the Rust application faster than C. Is that true? Any benchmarks for that?
There's a clarification. So concurrent Rust programs are almost certainly faster than C. And there is a very good example of this, which is ripgrep, which he mentions in the slides. Ripgrep is able to beat out Silver Searcher and GNU grep and a lot of other text searching algorithms, programs, even though it uses the same searching rules. So you can use PCRE, which those other programs use to search through. RipGrep outperforms all of them. And the way it does that is by having concurrency, but also having what Rust developers have described as fearless concurrency, where you're able to do certain things without having to worry about the possibility of deadlocks and data races, provided that you follow the safe programming standard.
I see. So what do you mean that with the Rust programming language standard that there might be a way you can avoid the log in a lot of cases?
Right.
Oh, I see.
Right.
Yeah, that sounds good.
So theoretically, of course, the C program could reach that same level of performance,
yeah.
But in a practical sense, it's difficult for a programmer to express that without being afraid of things crashing.
Yeah. Oh, by the way, I think you guys now support the Huawei Hikey 960 board.
That's right.
Yeah. So you can do some benchmark on that, actually.
Yeah, sure.
So, did you just say we support it?
Well, we're working on it. I mean, overpromise and underdeliver, right?
Work is underway. There's a student who's trying to bring up the stuff that we're doing on simulators on Hikey 960 and Hikey 620. But to set expectations, we're still a far way off from being at parity on what he's done with x86-64 on those boards, right? Yeah.
I don't think for the kernel is up, you can, when the kernel is up, you can start some micro benchmark. I think we will show something.
Yeah, that'd be interesting.
Yeah, so we have some tooling internally at ARM where we do benchmarking of this sort, and I'm very keen on seeing how the numbers stack up with some synthetic benchmarks at least between x86-64 and ARM. Okay. Thanks, guys. Thanks a lot.
Thanks.